So now that we've explored the true nature of the decimal number system, we can expose how binary numbers actually work, the secret of binary numbers. And here it is. The secret of binary numbers is they're no different than decimal numbers. Everything you already know about decimal numbers, everything that you know how to do with decimal numbers, addition, subtraction, multiplication, division, encoding values in decimal and decoding values from decimal, it's all the same in binary, except for one small difference. And that difference is that binary is base 2. While decimal is a base 10 positional numbering system, binary is a base 2 positional numbering system. And we also know that that base 2 means two things. First, binary uses only two symbols. It uses the 0 and it uses the 1. So binary is already simpler than the decimal numbering system. Remember that in the decimal numbering system, we use these 10 symbols, and we call these 10 symbols digits. Well, in binary, we call the symbols bits, which is just a mashup of the words binary and digits. So binary digits are called bits. We also have a word for a set of 8 bits. A grouping of 8 bits is called a byte. And we have another word for a grouping of 4 bits. A grouping of 4 bits is called a nibble. And this is roughly analogous to the way that we chunk decimal numbers in packs of 3, and we have our hundreds and our thousands and our millions and so on. The second thing that base 2 means is that the symbols 1 and 0 are placed in columns, and the columns are values that are powers of 2. Of course, by convention, we put the ones on the right, just like with decimal. And then 1 times 2 is 2, times 2 is 4, times 2 is 8, 16, 32, 64, 128, 256, 1024, and so on. And we encode numbers in binary in the same way that we encode numbers in decimal. So let's take a look at that. Here again are those two dice, the purple die and the green die. And we have 3 faces showing on each die, and we can count the pips. So 11 plus 6 plus 5 is 11, plus 3 is 14, plus 4 is 18, plus 2 is 20, plus 1 is 21. 21 pips on these 2 dice showing. And we can represent that in binary, just like we can in decimal, by placing one of these 2 symbols in each of these columns. And of course, in the 128ths column, we would put a 0 because there are no 128ths in 21. There are no 64s. There are no 32s, but there is a 16. So it's also interesting to note that there's always ever only one or none of a column value. There's not going to be 2 16s, for instance, because then there would have been 1 32. There's not going to be 2 8s, because then there would have been 1 16. And so again, binary is much simpler than decimal. And so if we take 16 of those 21, that leaves us with 5 left. So there are no 8s in that 5, but there's 1 4 in that 5. And that leaves us with 1 left. There are no 2s in that 1, but there's 1 1 in that 1. And so 16 plus 4 plus 1 is 21. It's the number of pips that are showing on these dice. And this is a representation of that value in binary. And it's fascinating, just as with decimal, we can use 10 symbols, and with just 10 symbols, we can represent any number. Well, it turns out that in binary, with just 2 symbols, arranged in columns whose values are powers of 2, we can again represent any number, an infinite number of numbers. And we talked about this with decimal. Conventionally, we do tend to use a minus sign and a decimal point for representing negative numbers and fractional numbers, but that's just a convenience. It's not necessary. With just 2 symbols, arranged according to columns that are powers of 2, we can represent any positive number, any negative number, and any fractional number. Again, I won't get into the details of how we do that. There are many ways to do that, and I'll leave that as a challenge for you to dig into. So,